Hi there. In this video series thus far, what we've done is that we have written the Fourier series for periodic functions that had a period of 2 pi. In fact, what we've done is that we have derived expressions for the Fourier coefficients a0, an, and bn, and all of these coefficients are only valid for a period of 2 pi. They have only been derived for this specific period. However, in reality, we have functions that have many different kinds of period. It's not guaranteed that the period of the function that we're considering is going to be 2 pi. So we have to now modify our work, modify the Fourier series, and modify these coefficients such that they can be applicable for any kind of period. So we can just consider some kind of periodic function. So it can look like something going through a cycle and repeating itself. So we said that the period is basically when the function starts to go through the same cycle again. So we'll just identify this point, and then we can see it goes through a cycle and then starts to repeat itself at a certain point later. So we could say in general that the distance between these 2 points is some kind of general period t, okay? So the first thing that we're going to do to try and modify this work is we're going to convert our axis, okay? We're going to change the independent variable. So previously the independent variable was x. So now we're going to change our independent variable to be t. So that means that y is now f of t. So let me just write down what we're doing. What we're doing is we're going to convert x to t, right? So why are we doing this? Well, we're doing this because we know the period is 2 pi, and we now want to represent t in terms of this 2 pi. So we're changing t to 2 pi. We need to convert we have to convert to be t to be in terms of 2 pi. So the way we do that is the first step is to change x from t, and we'll see just now where all of this is going. So now that we have changed x to t, and this whole thing is in terms of t, we can think about the period as being the time taken to complete one cycle, because this is now time on the x-axis. So I'll repeat once more that the period t is now the time taken for it to complete this cycle. So the period is this variable t, and what it is the time taken to complete one cycle. So there's our one cycle, and there's our time taken. So that's what the period is. So we can just give it a number, right? We can say that maybe it took 2 seconds, right? So our period is 2 seconds. It took 2 seconds to complete a cycle. So now what we want to consider is what happens when we invert this, right? So what happens when we invert this? So what we're now considering is the number of cycles in 1 second. So previously for the period, we have time taken to complete one cycle. So how many cycles are we completing in 1 second? So this is now what we're considering is the inverse of the period, right? So that is actually called the frequency. And it's the number of cycles divided by 1 second, and it's 1 over the period. And if we were to calculate it, we just gave the period a number. We said 2 seconds, so it's 1 over 2, and that's a half, okay? So what we're saying is that we're completing half a cycle in 1 second. So this number of cycles in 1 second, it's actually the unit hertz. So this is 0.5 hertz. So hertz is just the unit given to cycles per second. So the next thing that we're going to do is we're going to say, okay, because what we're doing now is we need to somehow relate this period to 2 pi. Everything needs to be in terms of 2 pi. So the next thing that we're going to do is ask ourselves, where do we see 2 pi and where does pi come up all the times? Well, it comes up all the time when we're considering angles. Remember that we express angles to be in terms of radians. And we said that, okay, we have pi radians, 2 pi radians, and all of these things. So that's where the period comes up. That's where we have 2 pi. And we now need to link this period to be in terms of angles, to be in terms of radians. So what have angles? So what has angles is a circle. So we can create an analogy here. If we think about it, we have a start point and we proceed and then we come back to our start point. So that is kind of like moving along a circle. Okay, that's a poorly drawn circle, but you get the idea. So we have a start point and we move, okay? So in the same way we have our cycle. We are now halfway along the cycle, we're halfway along the circle, and then we go back to where we started. So moving along this cycle is like moving along this circle. So this is now somehow talking to our 2 pi and our period and all of these things. So we need to bring in this period somehow into this concept of this circle, right? So we need to take 2 pi, and what we're saying is we have our start point along the cycle and we end up back at our start point. So moving along one cycle is like moving through this one revolution of this circle. And one revolution of this circle is 2 pi radians, okay? So in other words, to complete this one revolution, to complete this 2 pi radians, it takes 2 seconds. So this is what this period is. So we associate this 2 pi with this period. So this period is the time taken to complete this revolution of the circle. So that's the analogy at this point. So we could also say, okay, here is our start point and we move a distance, maybe t1 along this cycle, right? So we are now at this point and this is t1 units after our starting point. So that would be the equivalent to moving theta 1 radians along this circle, okay? So that's theta 1 radians, that's t1 after our start point. So that is this whole thing. So we create a new concept at this stage, or we rather define a new quantity, right? So this new quantity that we're looking at is, okay, so the revolutions, so one revolution is 2 pi radians. So how long did it take to complete this revolution? So it took the period t, so that's the time taken. So if you remember what speed is in general, speed is equal to distance over time. So this 2 pi radians is kind of our distance traveled in terms of the angle and this time taken in this period. So what we have created is some kind of speed, or rather some kind of velocity of the amount of time it took to move around that circle. So that is given a name, specifically the angular velocity. So that's the angular velocity. So with this angular velocity, we're saying that this is the speed it takes. So this is how the speed will move when it's going from its start to its finish around this entire cycle. So if you think about t1 and t1 again, so we said that this angular velocity is a constant, right? It's 2 pi over t. So it's a constant. So we said theta 1 is actually this 2 pi, so theta is the distance traveled. So instead of saying 2 pi, we have said some theta 1 distance later. And this time taken, it's equivalent. So we move along this, we move this t1 time later, and that's equivalent to this theta 1. So if 2 pi over t is a constant, it also must mean that it's equal to theta 1 over t1. Or not just theta 1 over t1, rather theta over t in general. So that's an important point, right? So what we're actually saying is that this unit time, so a unit time along our periodic function, is actually equal to the angle over the angular velocity. Okay, so in the same way, this angle is equal to this angular frequency times this time. So we're writing now the Fourier series in terms of the angle, right? So that is what we are writing the Fourier series in terms of, okay? So this now is actually equal to this angular velocity multiplied by time. And we know that this angular velocity is equal to 2 pi over t. So if we substitute that in, we get 2 pi t divided by this capital letter T, this period. So this is the key thing now. So this is what we're actually considering. So this is now the conversion. We have established some kind of relationship between 2 pi and t and small letter t and all of these things. So we have created now some kind, by using the circle as an analogy, we have linked all of these variables. We have linked this 2 pi and this period and all of these things. So if we now write this Fourier series, so this f of t, so this is our y value. And if we just remember what the Fourier series is, it's a naught over 2, then plus this sum where n starts from 1 and then goes to infinity of an cos. And now we're considering theta, okay? So instead of x, it's now theta. Because we said that we have this circle, and in this circle, we have our different variables. And since it's moving along this radial distance, that radial distance, the angle is actually x, okay? So we have linked that with t. So instead of theta, we can now replace that with 2 pi t over capital T. So we can write this as 2 pi n t divided by t. And we can do the same here. We have 2 pi n t divided by t. Okay, so this is our Fourier series in terms of our new variables for any period t. So the question is, what does our Fourier constants now become? How do we write our Fourier constants? If we just remember what a naught is, a naught we said was 1 over pi, integral from minus pi to pi. Remember our period is 2 pi. And we said f of x dx. So now we replace this with t and all of these things. So just a quick thing. Remember that our period is 2 pi. So we can just write 2 pi here, and remember that that's the period that we had previously considered, and we have to cancel out this 2, so we can put 2 in the numerator. So it's 2 over 2 pi. It's the same thing. So it's essentially the 2 over the period. So if we now generalize this to our new variables, we'll have a naught, and we have 2 divided by our period, so that's t. And now we have our integral. So instead of minus pi to pi, we could integrate from either 0 to t. So this is our new period. So t is our period. Or we could integrate, as we had done here, halfway between each of these things. So minus t over 2 to t over 2. As long as this length is the period t. And then we have f of t dt. So that's a naught. For an, if we remember what it was 1 over pi, and integral from minus pi to pi of f of x cos nx dx. So in the same way, this 1 over pi is the same as writing 2 over 2 pi. So we have now, in terms of our new variables, 2 over t, integrated from minus t over 2 to t over 2 of f of t cos, now not cos nx, but remember what we said earlier is that we now have cos of theta n, right? So we have 2 pi nt all over t. So that's what we're going to put in. 2 pi nt all over t and dt. And in the same way, we have bn. So bn will be 2 over t, the integral from minus t over 2 to t over 2, f of t sine 2 pi nt all over capital T dt. So we can just illustrate our new variables using a basic example. So we have done this example several times in different ways throughout the course of our work. So what we'll just have is some kind of function. So we have t, and here we have f of t. And then we have maybe minus 2, minus 1, 1, and 2, okay? So we can say maybe from minus 2 to 1, we have function value being 0, and then from minus 1 to 0, maybe it takes on the value of 1, and then it carries on from minus 1 to 1 with the same y value, and then drops back down to 0. So this is the periodic function, and this y value is 1. So let's write our Fourier series for this kind of function. So the first thing that we see is our period. So what is our period? We can see that our period is basically when the function starts to repeat itself. So it starts to repeat itself after 4 seconds. Okay, so it would take on this value again at this pointer, and it'll carry on like that. So from minus 2, we have 1, 2, 3, 4. So our period is 4 seconds. Okay. So now we can proceed with our work. We determine A0, and A0, if you remember what it was, we just wrote it, was 2 over t, integral from minus t over 2 to t over 2, f of t dt. So our period was 4, that's what we have just established. So we have 2 over 4, integral from minus t over 2 to t over 2. So t is 4, so we have minus 4 over 2. So we are integrating from basically minus 2 to positive 2. And then f of t is basically, we'll have to split this up. So it's going to be, function is 0, then it's going to be 1, etc., etc. So we're not going to waste time integrating this 0 here and this 0 here. So we're just going to integrate from minus 1 to 1 of the function value 1 dt. So it's going to be 0, integral of 0 is just 0, so, and then it's going to be 1 here and then 0 again. So it's just integrating from minus 1 to 1 of 0. So we get a half, and just integrating t from minus 1 to 1. So that would be a half into 1, and then we have a minus and a minus, so that's going to give us a plus. So 2 times a half is just going to be 1. So that's what an is equal to. Sorry, a0. So a0 is equal to 1. Now with an, we can just write it again. So we said that's 2 over t, integral from minus t over 2 to t over 2, and now it's f of t cos of 2n pi t all over capital T. So t is equal to 4. We're going to substitute it there, and we're going to substitute it there as well. So we have a half, and f of t is 1, so that's 1. So we're not going to waste time with that. So we're just going to integrate this thing directly. So we're going to have sine, okay, and we have 2 over 4, so that's a half. So we have basically pi over 2 essentially, right? So we're going to have sine of n pi over 2, and then we're going to have this t. And then we're going to have to divide this by what is in front here. So it's going to be n times pi over 2. And this is now going to be integrated from t over 2, that's 4 over 2, and carries on like that. But we know for a fact that okay, the function is 0 in these regions here. So we're actually just integrating from -1 to 1. So proceeding in this manner, what we're going to get is we're going to substitute all of these things in. We have a half into sine we're going to substitute t is equal to 1, so we're just going to get n pi over 2. And we have to remember here that sine of minus x is equal to minus sine x. So when we put in this -1 here, we're going to have sine of minus n pi over 2. So we're going to bring a minus in the front. However, there's already going to be a minus since we are integrating with respect to this lower boundary. So this minus in front now, with this minus, because we're integrating, is going to give us a plus. Plus sine n pi over 2. And all of this is divided by n times pi over 2. So we have 1 plus 1, so that gives us 2. So we're going to bring out this 2 in front. And now we have another 2 here, okay? So what's going to happen is that this 1 plus 1 gives us 2, that's going to cancel off with this 2, and then we take this 2 to the top, and we're just going to be left with 2. 2 sine n pi over 2. Okay, let's also not forget that we have to divide by this n pi. So sine of pi over 2, we need to look at some multiples here. So we have done this in the previous video, so we can just have a look at it quickly. So we have our function carry on like that. So that's pi over 2. This is 3 pi over 2. That is 5 pi over 2. So these are the x values, and that's pi, and that's 2 pi, etc. Seven pi over 2, and so on. Okay. So the first thing we see is that if we substitute in even numbers of n, we're going to have 2. So 2 times 2 divided by 2 gives us 1. So we just have sine of pi, and sine of pi is 0. If we substitute in 4, we're going to have 4 over 2. That's 2 pi. So 2 pi is also going to give us 0. So for even numbers, what this means is that an is going to equal to 0. Now let's look at odd numbers. So we have 1, 3, 5, 7, 9, etc. So if we substitute in 1, okay, so if n is equal to 1, we have sine of pi over 2. So if it's pi over 2, it's a positive number, so we just have 1. So this an is going to take on the value of 2 over n pi. If we substitute 3, we have 3 pi over 2. 3 pi over 2, we're going to get minus 1. Okay, so we have minus 1. So this value an is going to take on the value minus 2 over n pi. If we substitute in 5 pi over 2, we see we have a positive number, 2 over n pi. And it's going to be minus again. So every alternate odd number is negative. That's what we were saying. So what about Bn? Okay, so Bn is going to equal to 0. Why is Bn going to equal to 0? Because this function that we're considering is an even function. We said in the previous video that if it's an even function symmetrical about the y-axis, the Fourier series will only have cos terms. So that means that Bn is equal to 0. Okay, so we are done. We can just write our Fourier series now that we have all of this information. So we'll write f of t is equal to a naught. A naught is 1. A naught was 1. So that's 1 over 2. And now we have our constant, so we can just bring it out. So that's 2 over pi. So that's a constant. We can just bring it out, as we had done in the previous videos. And now we can write whatever is left. So we have cos. We substitute in n is equal to 1. So we have 1 over n, so that's 1 over 1. This is 1 in front. And our first constant is, remember, it's 2n pi t. 2n pi t divided by t. So essentially n is equal to 1 here. So we just have, and remember that we have t is equal to 4. So we have half. So 2 over 4 is half. We can just write the half here. Or let's just write it like this. So we have 2 in the denominator. And then we have n pi t. So we have just pi t. Then the second term is going to be negative. Remember, it's alternating. And we have 1 over n. So that's 1 over 3. And now we have cos. And 2n pi over t. So we said 2 over 4. So the denominator is 2. It's 1 over 2. And n is now 3. So it's 3 pi t. And it carries on like that. So the next term will be plus 1 over 5 cos of 5 pi t all over 2, and so on. So this is how we would write our Fourier series. So what we've done is that we have generalized our Fourier series to be in terms of different variables such that it can now be extended to any kind of new period t. So the important thing to remember is this new relations for this Fourier constant. So that is the main thing. Everything is exactly the same. We are still doing this work in this same manner. The only difference is now we're working in terms of 2 pi nt over some kind of general period t. So thank you very much for watching.